Welcome! In this video, we are going to discuss how to compute integrals fast. We will discuss a shortcut for linear substitution. So often in my differential equations classes, students have difficulty with computing integrals in such a way that it doesn't slow them down when they solve differential equations. So in this video, we are going to discuss a shortcut for linear substitution. So the shortcut is based on the following formula, which I'm putting in a box right now. So the meaning of this formula is the following. If capital F is an antiderivative of the small f, then we can compute this integral of f evaluated at ax plus b as 1 over a capital F of ax plus b plus a constant. We are going to consider several examples, and it is actually not necessary to memorize this formula. We are going to do so many examples that after doing all of these examples, you will get an idea about how to apply this formula without even really memorizing it. However, before we go to examples, I always like to explain why is this true. Because in mathematics, things are true not because a professor tells you that they are true. There is always a logical reasoning behind every formula. So you may remember that if you wanted to do a substitution in this integral, and if the substitution was supposed to be u equals to ax plus b, we would have to compute something that is called du. And this du is going to be the derivative of u with respect to x dx. So if we look at this expression right here, the derivative of this expression with respect to x is just a. So this is going to be a dx. So we know that du is a dx, which means that dx is 1 over a du. So then we can go back to this integral and say that this is integral of f of, and now instead of ax plus b, we are going to write u. So this is integral of f of u. And then instead of dx, we are going to write 1 over a du. And I'm going to put 1 over a in front. So this is going to be 1 over a du. Now, if capital F is antiderivative of this small f here, this is going to be 1 over a capital F of u plus a constant. And if you remember, when we do a substitution to compute an integral, we always have to come back to the original variable. So now, instead of u here, we should plug in ax plus b. So in the end, the result is going to be 1 over a capital F of ax plus b plus a constant. Okay, so just to be sure, this is the substitution, and this chain of inequalities continues over here. And then if you compare the first integral over here with the first integral in the formula, you will see that they are the same. And then in this chain of inequalities, the last expression is the same as what we see on the right-hand side of this formula in the box. All right, so we have explained why this formula in the box is true. Let us now go ahead and do a few examples. So let us now consider an example. Let us apply this formula that we have here to this specific example where we want to compute integral of 1 over 2x plus 3 dx. So let us recall that integral of 1 over x dx is ln of absolute value of x plus a constant. So in this formula 1, the little f of x is 1 over x, and its antiderivative is natural logarithm of absolute value of x. And then in formula 2, we are looking at this expression here, 2x plus 3, right? So we have 1 over 2x plus 3 can be written as f of 2x plus 3, which looks exactly like what we have in this formula 0 on the top. Right, so we are just trying to see how this formula 1 can be applied in this situation when we want to compute integral 2. So we figured out that in this integral, little f of x is 1 over x, capital F of x is ln x, right? So ln x is antiderivative of 1 over x. However, we do not have 1 over x. We have 1 over 2x plus 3, which is f of 2x plus 3. So that means that ax plus b for us is 2x plus 3. So then by formula 0, we can take integral 1 over 2x plus 3 dx. It's going to be, so if there was no 2x plus 3 in the denominator, if there was just x, the integral would have been ln x. But because there is 2x plus 3, the integral is going to be 1 over a. So a in our situation is 2, so the integral is going to be 1/2 ln of 2x plus 3 plus a constant. All right, so now we have computed the integral that we wanted to compute, right? This was our goal, and we did compute the integral. We found what it is. So you may want to ask, well, it did take us a while, and it doesn't seem like this path was any shorter than it would have been to do the substitution u equals to 2x plus 3. And you would be right here. But the goal of this video is for us to learn how to do these shortcuts faster. So if we didn't have to go through this comparison of the integral 2 with how it fit with the formula 0, we could actually compute the integral much faster. So this is how we can compute the integral much faster. So we have integral of 1 over 2x plus 3 dx. And we see that we have a linear expression here, 2x plus 3. So whenever we have something like that, we may wish to think, well, what's going to happen if we just denote this linear expression by u? So if we had integral of 1 over u du, that would be an ln of u plus a constant. But we do not have a u. What we do have is 2x plus 3. And remember, the coefficient near x is 2. So this is why this original integral of 1 over 2x plus 3 dx is going to be 1/2 natural logarithm of absolute value of 2x plus 3 plus a constant. So now you can see that we can compute this integral much faster as long as we realize what is going to be the antiderivative of the function if we denote the linear expression by u. So now let us consider the examples that are outlined here, A, B, C, and D, and we are going to apply the shortcut that we have just learned to these integrals. So here, let us recall, if we had integral of 1 over u du, it would just have been ln u, and u, remember we have an absolute value in here, plus a constant. So this would be 1 over 1/2, and this is because there is 1/2 in front of x, ln of absolute value of 1/2 x minus 5 plus a constant. And so then 1 over 1/2 is just 2, so we have 2 ln 1/2 x minus 5 plus a constant. So how about this example A? Wasn't it faster than doing a substitution? I hope that now we can see the idea, that it helps. So now let us look at this integral here. If we had integral of u to the 5th du, the antiderivative would have been u to the 6th over 6 plus a constant. So if we come back to our integral, we will have 1/3, where 3 is coming from here. And then we will have 3x minus 7 to the 6th over 6 plus a constant. So overall, this is going to be 3x minus 7 to the 6 over 18 plus a constant. How was that? Now, let us look at this example C. So we have an integral of cosine u du. That would be sine u plus a constant. However, we have cosine of 7x. So we're going to have 1 over 7 sine of 7x plus a constant. This was very quick, wasn't it? Now, here we have integral. So if we had 1 over u squared plus 1 du, that would have been arctangent of u plus a constant. However, instead of u, we have 2x minus 3. So we're going to get 1/2 arctangent of 2x minus 3 plus a constant. All right, I hope that these several examples were helpful for us to learn how to compute integrals quickly. So this was devoted to linear substitution. The reason why we call the substitution linear is because this function over here, the one I'm highlighting right now, so this function here, ax plus b, it is linear. So this is why we call this substitution linear. If you liked this video, please hit subscribe to support making of more of these videos. Please put a like on this video so that YouTube promotes these videos and other people are more likely to see them. And please write a comment if you have any questions or if you have any suggestions about what the future videos should be about.